By 1940, the piston engine was shocking on its own complexity. The pursuit of horsepower had become a pursuit of density. To go faster, designers were adding cylinders, increasing manifold pressure, and complicating valve gear. The apex of this philosophy was the Napier Saber. It was a 24-cylinder H-pattern sleeve valve monster. It produced over 2,000 horsepower, but it required manufacturing tolerances that bordered on the impossible. It was a watchmaker's nightmare at £2,000. Frank Halford designed the Saber. He knew better than anyone that the reciprocating internal combustion engine had reached its thermodynamic and mechanical asymptote. You could add more cylinders, but the friction losses and cooling drag would eat the power gains. The limitation wasn't fuel, it was the mechanics of reciprocation. Stopping and starting heavy metal pistons 3,000 times a minute was an engineering dead end. To understand why Halford abandoned his own masterpiece to look for something else, we must understand mean effective pressure and piston speed. Power in a piston engine is a function of torque and RPM. To get more power, you spin it faster. But piston speed is limited by the tensile strength of the connecting rods and the ability of the valves to flow air. The Saber solved this with sleeve valves, sliding cylinders that eliminated valve float. But the heat rejection required massive radiators. The drag penalty of cooling a 2,500 horsepower piston engine at 400 miles per hour cancelled out nearly 30% of the thrust produced. Halford recognised that the piston engine was fighting the air, not using it. The aircraft needed a prime mover that didn't require intermittent combustion. It needed continuous thrust. Frank Whittle had already proven the gas turbine concept. The Powerjet's W1 was running. But when Frank Halford, an independent consultant working for de Havilland, inspected Whittle's engine, he was offended as an engineer. Whittle's design used a reverse flow combustion system. Air entered the compressor, it was thrown outward. It was piped forward, against the direction of flight, into the combustion chambers. It made a U-turn to pass through the turbine. To Halford, this was parasitic loss. Every bend in the ducting represents a pressure drop. Every change in velocity vector was wasted energy. The Whittle engine was a centrifugal pump, fighting its own plumbing. It was wide, it was inefficient, and the airflow path was tortured. Halford's critique was simple. If the aircraft moves forward, the air inside the engine should move forward. Frank Halford was unique in British aviation. He didn't work for the manufacturers, he leased his intellect to them. He had designed the BHP engine in World War I and the Gypsy series for light aircraft. He was a pragmatist. In April 1941, Halford gathered his small design team. He didn't want to improve Whittle's engine, he wanted to clean it up. His concept was the H-1, later known as the Goblin. The design philosophy was straight through. Intake at the front, compressor, combustion, turbine, exhaust. No U-turns, no reverse flow. A straight line of high-velocity gas. To achieve straight-through flow, Halford had to make a critical engineering gamble regarding the compressor. Whittle used a double-sided impeller. It sucked air from the front and the back to balance the loads. But this required a complex plenum chamber to get air to the back of the compressor. Halford opted for a single-sided centrifugal impeller. It would take air only from the front. This allowed for a direct, high-velocity intake duct from the wing roots of the aircraft directly into the engine face. The physics advantage? Ram recovery. At 400 miles per hour, the air ramming into the intake is already pressurized. A straight duct preserves that pressure. A plenum chamber destroys it. The physics disadvantage? Axial load. With a double-sided impeller, the vacuum forces cancel each other out. With a single-sided impeller, the engine is trying to suck itself forward violently. The entire thrust load of the compressor, tons of force, would sit on a single thrust bearing. The design was elegant on the drawing board. A single rotating assembly, one moving part. But the temperatures required to make the cycle efficient, over 700 degrees Celsius at the turbine inlet, combined with a rotational speed of 10,500 RPM, created a material nightmare. The centrifugal force on the turbine blades at that speed is roughly 10,000 times gravity. A 1 ounce blade weighs 600 pounds. At 700 degrees Celsius, steel becomes plastic. It stretches. This is creep. If the blades stretched even a millimeter, they would grind into the casing, disintegrate, and turn the engine into a piece of shrapnel. Halford had the aerodynamic theory, but in 1941, he did not have the metallurgy to keep the H-1 from tearing itself apart. How the H-1 Goblin survived the combination of centrifugal stress and thermal shock. The H-1 Goblin was designed to consume 60 pounds of air per second. The heart of the beast was the single-sided impeller. It was machined from a solid forging of aluminium alloy, RR59. The problem was diameter. Because it was single-sided, it had to be larger than Whittle's to move the same amount of air. A larger diameter means higher tip speeds. At full power, 10,500 RPM, the tips of the impeller were travelling at supersonic speeds relative to the air. Halford's team had to design diffuser vanes to catch this supersonic air and slow it down to convert velocity into pressure. If the gap between the spinning impeller and the stationary diffuser was off by a fraction of an inch, the air would detach, causing a compressor stall, a violent reversal of airflow that sounds like a shotgun blast and can snap compressor blades. Once the air is compressed, it enters the combustion chambers. Halford couldn't use a single annular ring, common today, because the manufacturing tech didn't exist. He used cans. The H-1 had 16 combustion chambers. They looked like flower pots. The engineering challenge: flame stability. The air is moving through the chamber at hundreds of feet per second. Trying to keep a flame lit in that airflow is like trying to keep a match lit in a hurricane. Halford's solution was the swirl vane. He introduced the primary air through a swirler, creating a vortex. This vortex created a low pressure zone in the centre that recirculated hot gas back toward the fuel nozzle. This recirculation anchored the flame. If this failed, the flame would blow out. If it worked too well, it would burn the metal walls of the can. It was a tuning process involving purely empirical testing, drilling holes, running the engine, melting the can, patching the holes, and trying again. The turbine blades remained the critical failure point. Standard austenitic steels used in piston engine valves failed within hours. The solution came from the Mond Nickel Company. They developed a nickel-chromium alloy called Nimonic 80. 80% nickel, 20% chromium, trace titanium, and aluminium. Nimonic 80 didn't just resist oxidation, it resisted creep. It maintained its crystalline structure under high stress at 750 degrees Celsius. Halford's design required the blades to be attached to the turbine disc using a fir tree root fix. This mechanical interlock allowed the blades to expand loosely when cold and lock tight under centrifugal load. The engine ran. On April 13, 1942, the H-1 roared to life. It was immediately more powerful than Whittle's engine, producing 3,000 pounds of thrust. But the single-sided impeller created the exact problem critics predicted: thrust loading. The engine was generating 3,000 pounds of thrust out the back, but the suction at the front was pulling the rotating shaft forward with massive force. Standard ball bearings failed instantly. They overheated and welded themselves together. Halford's team had to design a cooling system specifically for the bearings, bleeding cool air from the compressor to wash over the rear bearing housing. If this airflow was interrupted for even 5 seconds, the bearing would 16 and the shaft would shear. The engine was ready, but it was useless without an airframe. Halford was in a unique position. He was designing the engine and consulting on the aircraft simultaneously. The aircraft was the de Havilland DH-100 Vampire. Because the H-1 used a straight-through design, the exhaust exited directly behind the turbine at high velocity. You couldn't put a tail behind it, it would melt. This dictated the aircraft's geometry. short fuselage pod for the engine, twin booms to hold the tail surfaces out of the jet wash. By 1943, the H-1 Goblin was the most powerful jet engine in the world. It was simpler than the German Jumo 004 and more efficient than the Whittle designs. But successfully running on a test bed is not the same as flying. The engine now had to prove it could operate not just at full throttle, but at altitude, where the air is thin, the cold is extreme, and the flame is prone to dying. Halford had built a machine that worked on the ground. Now he had to prove it wouldn't kill pilots in the stratosphere. How the Goblin defined the first generation of jet warfare, and why Halford's simple philosophy won. The H-1 Goblin was the first jet engine to pass the British military's type approval test. This was a grueling 100-hour endurance cycle. German engines, Jumo 004, had a service life of 10 to 25 hours. The Goblin was certified for hundreds. The performance metrics were staggering compared to the piston engines Halford had spent his life building. Napier Saber, 2,400 pounds weight for 2,200 horsepower equivalent. Halford H-1, 1,600 pounds weight for 3,000 pounds thrust, roughly 4,000 plus horsepower at high speed. The power to weight ratio had doubled. The vibration was gone. The torque reaction that made piston fighters hard to handle was gone. The Goblin was so successful that the Americans wanted it. The first prototype of the Lockheed XP-80 Shooting Star, the first operational US jet fighter, didn't fly with an American engine. He flew with Halford's Goblin. This highlights the strategic gap. General Electric was still struggling with the plumbing of the Whittle-derived engines. Halford's straight-through design fit perfectly into the fuselage of the P-80. On January 8, 1944, the Goblin powered the XP-80 to 500 miles per hour. It proved that the straight-through axial installation was the future of fighter design. Back in Britain, the H-1 Vampire became the first aircraft to land on an aircraft carrier, and the first to cross the Atlantic. Why? Reliability. The Goblin didn't have the highest compression ratio, it didn't have the highest thrust, but it didn't flame out. Halford's decision to use a large, single-sided centrifugal compressor meant the engine was tolerant of dirty air. It could handle bird strikes and ice ingestion better than the fragile axial flow engines the Germans were building. The Vampire could hover at 40,000 feet. At that altitude, piston fighters were wasting for air. The Goblin was thriving. The single-sided intake utilised the ram effect efficiently, maintaining compression even in the thin upper atmosphere. Halford took the logic of the Goblin and scaled it up. The result was the de Havilland Ghost. This engine powered the de Havilland Comet, the world's first jet airliner. The lineage is direct. The engineering principles Halford established with the H-1, straight-through flow, single-sided impurity, high-velocity exhaust, made commercial jet travel possible. While the Comet airframe had structural flaws, fatigue, the Ghost engines were flawless. They run for thousands of hours with minimal maintenance. Eventually, the laws of physics caught up with Halford's design. The centrifugal compressor has a frontal area problem. To get more power, you need a bigger diameter, which creates too much drag. The future belonged to the axial flow engine, small diameter, multiple stages. A Halford design eventually adopted with the Gyron. But the Goblin holds a specific engineering title. It was the bridge. It was the machine that proved the gas. The turbine wasn't just a scientific curiosity, but a reliable prime mover. Frank Halford started his career building the most complex piston engines in history. He ended it by building the simplest jet engines possible. He realized that in engineering, complexity is not a virtue, it's a tax. The H-1 Goblin was a triumph because it had one moving part. It turned fuel into noise and thrust without argument. Halford didn't just design an engine, he designed the death certificate of the piston age.